Chapter 13, Equilibrium. Well, this chapter is a 100% problem-solving chapter for you. There are no new equations. None. Zero. Not even one. But it's an applications chapter, so the problems will be a little longer and incorporate more than what we have seen up until this point. Well, equilibrium, we already know for translational motion, sum of the forces equals zero. That means you are in mechanical equilibrium for translation. Well, mechanical equilibrium for rotation means sum of the torques equals zero. And as I have down here, both now must be true for a particle or structure to be in equilibrium. And why is this important? It is mostly, often, used for structural stability. And here we have kind of a dynamic structural stability example of an airplane. So I realize we are not studying aerodynamics, but I think we know enough about forces and torques to appreciate that if the center of mass of a plane, so the weight distribution of the plane, is slightly off of the front wings, the lift force that the wings generate to allow the plane to fly will also generate a twisting torque based on the fact that center of mass is nature's point of rotation. Let me zoom in here because it's kind of a little r, but if we have an r, right, cross F, you get a twisting torque in a counterclockwise direction. And that plane is not stable. Even if the center of mass is even closer, it's going to be a very wobbly plane. So that tail force, as I have shown here, so it's in green, so let me keep it in green. The tail force down, right? Now let me put my R in red. So if we have an R, and let's do it. And slide the R vector over, and we'll do it formally. R cross tail force F, that's going to create a stabilizing force to balance the torque that the force lift is generating. So it is critically important anytime you are interested in the overall stability of any structure that you look at both the forces and torques that are occurring on that structure. Well, again, there's nothing new here. We knew from translational motion that you have both static and dynamic equilibrium, meaning that sum of the forces equals zero, right? Sum of the forces equals zero does not necessarily mean the object is not moving at all. What it means is that the acceleration is zero, so that it is either at rest and staying at rest, or the object is moving at a constant velocity. Now, notice we also have our Newton's second law momentum form, delta P over delta T here. So another way of looking at equilibrium is to talk about conservation of angular momentum. So when a system is in equilibrium, its momentum is conserved, both in terms of angle and translation. And that, of course, would refer to dynamic equilibrium because there's no momentum to talk about in static equilibrium. So as I said, we are going to look at two examples together here in the notes that are a little more involved than the problems we've looked at up until this point. But you now have a whole toolkit of equations and analysis that we've used to be able to problem solve and understand these problems that are a little more involved. So that's it for our introduction. It kind of gives you a feel as to where we're going. Our next couple of lessons will look at some numerical examples and you'll get a much better feel.